My name is Chris McLaughlin, Honorary Secretary. At this stage, I think we have a quorum of attendees, so I'll pass on to the Chair of the Ireland Network, Aidan Langley.
Thank you, Chris, and welcome everybody this evening, particularly to the people from Engineers Island in Cork. And I'd like to introduce Jeffrey Godsill, and thank him in advance for organising the event this evening on the webinar. So Jeffrey, over to you.
Thanks for that, Aidan. So everyone, you're all very welcome here this evening, and it gives me great pleasure to introduce Rory. So Rory and I go back quite a few years, and when I first approached Rory about giving tonight's lecture, probably 12 months ago, he didn't hesitate. So we're fortunate to have a speaker with Rory's depth of experience. For the past 7 years, Rory's been working with BGE, Bord Gáis Energy, in Whitegate Power Station. His most recent role is in the Asset Operations Department, where he has a very wide remit. And Rory looks at all aspects of plant operation, outage coordination, etc. Prior to joining BGE, Rory worked for approximately 10 years with the Irish TSO Airgrid. First 5 years of that, Rory's working in the Protection Department. And in the Protection Department, Rory had a very wide, I suppose, range of tasks, looking at fault studies, he looked at relay settings, reporting system disturbances, and the list goes on. The next 5 years of his time in Airgrid, he progressed into the National Control Centre, where Rory worked on shift and had the responsibility for literally keeping the lights on. So while tonight's webinar focuses on Whitegate Power Station, I think it's fair to say that we have a real expert on our hands with Rory. So I'd encourage everybody to make use of the facility to raise questions, and hopefully we'll have a lively Q&A session at the end. So without any further delay, I have great pleasure in handing over to tonight's speaker, Rory. So thank you.
Right, thanks Jeffrey for the kind introduction. I'll just share my screen here with you guys, just so you can see. Right. Okay, so hopefully you can see my screen there. So I suppose thanks Jeffrey for the introduction. I suppose just to reiterate, I suppose I have nearly 17 years experience, and the last 6.5 I've been on the power gen side, which is quite a change from the transmission. So just to give you a flavour for tonight, I'm going to discuss a bit on how the station came to be for Bord Gáis Éireann at the time, how we operate the asset operations team, the model we have, how the station actually works. And then at the end, we'll have some time for questions as well from yourselves. So I suppose just to maybe add to what Jeffrey said, at the time I joined Bord Gáis Energy, there was a lot of change, I suppose, in the Irish energy market. The rock-off study with Airgrid had just kicked off for generators to try and facilitate more renewables. So I suppose my joining the generation team was a little bit timely. And also then, since then, there's been, I suppose, a number of DS3 tenders, bits and pieces like that, as well as the normal day-to-day stuff. So certainly having the grid experience helps me in the current role. So we'll just go from the start really, and how Bord Gáis Éireann came to have an asset. So back in 2004, Bord Gáis Éireann was developing a dual fuel strategy. The gas market was deregulated, which meant, I suppose, for Bord Gáis Éireann that some of the competitors would start picking up some of the gas customers. So I suppose to compensate that, they wanted to get into the electricity market. So having an asset was going to underpin this strategy. So Bord Gáis Energy was created, and you may recall at the time the Big Switch campaign, where I suppose Lucy Kennedy was going around putting switches on the end of houses, trying to entice people to Bord Gáis Energy. So that would have been around the same era. So when the question then came to where would we, I suppose, build an asset. So if you were building a power station today, the Dublin area, notified here by these green nodes, would be quite welcome. Cork area at the moment, with the red there, it's kind of showing signs of a constrained network, similar up by Mayo there. So really what you're seeing there is on the west coast of Ireland, there's a lot of wind. And in Cork, then there's a lot of generation with the Whitegate asset and also the ESB asset next door, the AHDA 2 unit. And more recently on SSE have a new CCGT down near Waterford. Now, back in 2004, such a map wasn't available. So the guys in the Bord Gáis Éireann office in Cork pulled out the next best map they could find. And really, there was only one option. So they decided to build in Cork at the time. They didn't know about all this wind that was coming down the track. So the Whitegate site became available in 2005. I'll just show you here. Hopefully you can see this on your screens. So the site itself is up next to the Whitegate oil refinery. Just right here, it's 25 acres of industrial site, and I suppose the good thing here was already industrially zoned. It was reasonably close to an electrical connection. So down at the ESB station at the bottom right of the screen here, there is a 220 kV station there. So it wouldn't be too long to have an immediate connection, but as ESB were also developing their own asset, a bit more reinforcement was needed in the network. So there's also a cable under the harbour across towards Carrigaline to the Rafine station, and also from the ESB station, there's also a second cable going across the harbour. So quite a lot of developments back in, I suppose, from 2007 to up to 2012, really, when the cables were finally brought into service. Just some other points to note here. Having a refinery next door to us is very handy. In the Irish Grid Code, a gas-fired station such as Whitegate or the other CCGTs have to be dual fuel. So in the event there was an issue on the gas network, the units would be expected to switch over to secondary fuel. This would help retain the gas pressure for domestic customers as well as business customers. So the site itself was quite handy. The one thing that was missing was a decent gas connection down to the Whitegate area. Up the road at Middleton is quite a strategic node on the gas network. You have the compressor station there, which I suppose historically was used to pump gas into the Kinsale field in the summer months and take it out again in the winter. So ESB and Bord Gáis Éireann, they developed a pipeline down to support the two new units. So let's get some drink of water there. So just on this slide here, I'm just going to go through a couple of key dates. So the last day we mentioned was 2005. So by August 2007, an EPC contract was awarded. So EPC stands for Engineer, Procure and Construct. And I suppose the Bord Gáis energy model, like they wouldn't have the power gen heritage like say ESB would. So as part of their model, they also awarded an operations and maintenance contract to GE. So the construction would have been GE Gamma partnership. And then once the plant was fully built and commissioned, ESB then, or GE, apologies, would also then take over the day-to-day operations at site, managed by two contracts. We'll touch on them in a second. So by late 2007, the site was mobilized and some of the civil works started mapping out the different areas at the site. If you fast forward to January 2009, some of the large equipment started arriving to the site. So here you see the gas turbine on its way up to the site. We'll discuss this in more detail when we're covering how the unit actually works. But to give you a little bit of perspective, you can see how big it is next to the house there. February 2010, the gas turbine first fired, and then it went through a fairly lengthy commissioning phase, and it finally went into commercial operation in November 2010. So I have some other dates here, just some of the milestones in terms of the maintenance inspections on the unit. So in September 2011, it did its first borescope inspection. So this is where you get a camera. Now when I say camera, it looks more like it's an optic fiber camera, but it's on like a long rope for want of a better description. And you can remove plugs in the machine and you can get the camera in, you can get a look at the blades. So really what you're doing is having a good look in around the unit before your next larger outage. So the following year, in May 2012, we went into a combustion inspection. Here you have 18 combustion cans around the unit arranged equally around it, and therefore at the time every 12,000 hours in the machine you would change these out. And if we go then to May 2014, the first hot gas pad inspection, so this interval will be 24,000 hours on the machine, and in this outage the combustion cans were changed out, but also the blades on the gas turbine, and also then there was an inspection on the compressor blades. And in parallel with that, then there was a minor inspection on the generator and a minor inspection on the steam turbine. So the bearings would have been looked at. It's worth mentioning around 2014 that Bord Gáis Energy was sold. So 3 buyers came in as a consortium as such, where Centrica bought the Whitegate asset and the gas and electricity customers and retained the Bord Gáis Energy brand. Brookfield Renewables came in and bought the Borgosh Air and Wind Farms, and Icon came in and bought Firmus Energy in Northern Ireland. The last of the milestones on this slide then is the first major inspection in February 2018. This covered, again, the combustion cans would have been changed out in the machine, the gas turbine blades, the first major inspection on the steam turbine. So the covers were lifted for the first time. An assessment was then taken on the rotor of the steam turbine as well as the bearings. And we did a more detailed inspection on the generator as well. So how we operate then. So as I mentioned, GE have an operation and maintenance contract. So this is the day-to-day operations at the site. There's 31 staff, so that's kind of typical for a plant of its size, quite lean in numbers. And you have an operations team doing shift work. It's 24/7 operation. They work 2 days, 2 nights, 12-hour shifts, and then they have 4 days off. So I suppose it's probably worth mentioning the last couple of months with the COVID impact. This hasn't affected the operations staff as such. They're still working the same shift patterns, but the rest of the staff, maybe it's similar to yourselves at home. A lot of the admin staff are working from home, and the maintenance team have been split in two, so there's segregation there, and obviously social distancing has been maintained at all times. So I suppose where the asset operations team in Borgosh, where we sit, is the GE remit kind of stops at the station gate. So anything outside the gate, whether it's license compliance with the grid code or generation license with the CRU, the commercial aspect of it. So like, I suppose I'm kind of like the link and the team between the asset and the trading team in the new ISIM market. We're also looking ahead to ensure like we've a robust asset management in place, particularly around the boiler as the plant starts to age and maybe starts stopping and starting more. And I suppose we also ensure, alignment with best industry practice as well as the expectation of the Centrica parent company. The second contract, the contractual service agreement, this is a bit like, I suppose an easy way to describe it is a bit like your car insurance. So we fully comp insurance on the gas turbine and the steam turbine. So parts, labor, and we pay for this. So we kind of pay for it in quarterly fees. And on the generator itself, we only have an inspect only. So any parts needed for the generator, they will be to our account. Both contracts are 12 years, as I kind of mentioned. They were recently renegotiated, so they're both up to roughly 2030 at the moment. Now, I appreciate many of you might have different backgrounds. So in terms of 450 megawatts, like what does a megawatt power? So basically, I've looked at different, I suppose, brochures and literature over the years. So like, for example, when the East-West interconnector was being commissioned, it was X number of thousand homes. Different assets get commissioned. You see these kind of headlines. So I kind of had a look at it, and 1 megawatt is roughly 650, 660 homes on the island of Ireland. We've done this slide in the past with GE guys in the room. So the next few bits of equipment are all GE, just that was kind of to keep them happy. But a standard wind turbine, you might see, there'd be 2 to 3 megawatts. They're always getting bigger, particularly the offshore ones. But as you look around Ireland, you're in around 2 to 3 megawatts. A Boeing 777, there's 75 megawatts of power on the jet engines there. Aircraft carrier, a bit bigger again, 190. And then I suppose Whitegate at 450, you're in around 300,000 homes. I suppose personally, 300,000 homes, it's a bit subjective. The way I look at it is, if you're looking at the size of Ireland in terms of demand, and you factor in, I suppose, both jurisdictions in the ISIM market, Northern Ireland and the Republic, you're roughly a 7,000 megawatt system in the peak. But typically a lot of the year the demand is a bit lower than that. It could be in around 4,500. So there's times when Whitegate on its own could be up to 10% of the demand. Other times it's around 4 or 5% at bigger demand periods. Then I suppose I'm just going to maybe highlight some of the key stakeholders we have just in day-to-day operations. So Irving Oil at the refinery, they're both our landlord and also our fuel supplier. So I kind of mentioned a unit like Whitegate would have to hold, up to 5 days running on secondary fuel. I suppose on the electrical side then, both EirGrid would operate the system, and ESB Networks, it's their assets outside of our transformer on the HE terminals. And we're quite fortunate for a new connection to have 2 cables the cable down to the AHATA station and across the harbour. Each of them on their own, you can get the full output of the unit. So you know, if one's on maintenance outage, we're not constrained in any manner. On the gas network side, we're connected to the mains gas network. I think it's designed up to 85 bar pressure, but typically it's down around 58, 60 bar in Cork, and that's up to the Middleton station. I'm sorry, go back there. And key to a power station, which we'll see in a second, is the water supply. So we're limited to take in 10 tons per hour on our license. And then finally, with the EPA, our emissions, etc., our groundwater, all this is monitored. So we'd have ongoing interaction with the EPA, and then of course the Health and Safety Authority, if needs be. So how does it actually work? So what I'm going to do is I'm actually going to move to kind of an interactive presentation, which we normally give with the site tour. Maybe just if you're at home, make sure your screen is maximized just so you can get the most out of it. And I'll just switch over to it here. So one point actually I failed to mention is it's actually a GE machine. Probably wouldn't have looked good if we had GE and Gamma constructing the site. We got GE to operate it and we had a different machine itself. So we have a GE gas turbine, we have a GE steam turbine, and a GE generator. The boiler we'll cover in more detail. It's a CMI boiler. And I suppose for those of you not familiar with Cork, Whitegate itself is located about 25 miles east of Cork City, just at the entrance to the harbour. So in this picture here, what we can see is the gas pipeline coming in. This installation here, this is called the above ground installation, the AGI. This is only Gas Networks Ireland staff go in here. The guys in the day-to-day operation don't go up here at all. So this is a bit like an embassy. So this is the Gas Networks connection. So the gas comes in at, you know, say 58, 60 bar pressure. It comes through our reducing station and we drop it down to about 35 bar pressure for the gas turbine. So from here, it kind of follows this path around the site. Just something to bear in mind, the gas itself, we actually have to preheat it up to 200 degrees Celsius. So we take intermediate pressure feed water, which I'll explain in more detail in a short while. So we preheat the gas fuel because as you drop down the pressure, you'll reduce the temperature as well. So the gas turbine is kind of high maintenance. It needs everything spot on. So this is the requirements we have here with the gas. Just, I suppose, one other thing to point out is gas that's coming in, that's metered, it has a content of water. So as soon as that gas is put to the gas turbine, the water content is flashed off. So you have about 90% of the volume of gas that comes in. So you have the higher heating value here. And when you lose the water element, it's a hydrocarbon, you have the lower heating value then actually being used in the gas turbine. So just in case you come across those terms, that's a small bit of context there. On the electrical side, our generator is located here in the turbine hall. The terminals of the machine are at 19 kV. So the 19 kV bus ducts come out here to the side of the building. They come down here to the step-up transformer. They're stepped up to 220 kV. Then there's a 220 kV cable just coming around the site here to the GIS building. So this is our electrical connection to the grid. Again, a bit like the AGI, only, I suppose, teams from ESB Networks, Airgrid, or ESBI commissioners usually would be in here. Again, the site team would not be inside here. So it's a bit like, again, like a second embassy. From here, the two cables come out here and then they split in different directions. One heads down to the shore to cross the harbour, and the other cable makes its way down to the ESB site at AHATA. I suppose one thing to point out, when Whitegate first commissioned, it did have a temporary connection. So you had this compound here. This is air insulated switchgear. I suppose it's out in the open. And finally, then when the GIS was commissioned, the connections were moved here, and this now is redundant. These are the original construction offices, and we still use these to this day. They're quite handy actually during maintenance outages because we've quite a lot of space in the site. So as contractors come in, we can house them in different locations here, canteen facilities, etc. So I'll just move on now to the actual site overview itself. So I suppose I'll just start up in the top corner here and we'll just give you a feel for what's what. So as mentioned, we can take in up to 10 tons per hour raw water from the local supply from Irish Water. This is drinking water, but it's not clean enough for the machine. So we pass the raw water through the treatment plant, and there's filtration. We add various chemicals to it and we come out with pure H2O. And once the H2O is created, it's stored here in the demineralized tank. This then is what's used to supply into the machine. And next to these tanks, we have the workshop and store. There's also the canteen, locker rooms, etc., first aid room. And here is the administration building. So the control room for the plant is here, as well as some of the site offices for meeting rooms, plant manager, operations manager, and the rest of the team, etc. Coming along the side here, just to give you bearings, this will be south-facing side of the site, and this will be the north-facing side over here. This is the electrical building, so there is lots of pumps, motors, fans, etc. on the balance of plant. So the balance of plant would be the term used for outside of the center line. So these are all supplied here from the electrical building. The house supply is typically 1.5–2%. So what I've quoted Whitegate as a 450 megawatt unit, its minimum level that's stable is 160 megawatts. So you're down around maybe 4 megawatts of house load. So there's quite a lot of I suppose energy at the site itself, mainly in the feed water pumps and the condensate extraction pumps. And when the plant then is up closer to maximum output, this house load increases to maybe 8, 9, 10 megawatts depending. This is the filter house for the air intake to the compressor. We'll discuss that shortly. And down here in the bottom of the screen here is the auxiliary boiler. So the auxiliary boiler is key to the plant actually starting up. So if Whitegate's in an offline state and it gets an instruction from grid to come on, first thing that happens is the auxiliary boiler started up. It produces steam, which is used then to pull vacuum and also to provide seals on the steam turbine. If the auxiliary boiler doesn't start, Whitegate isn't coming on basically. Along the bottom here then, we have fin fan coolers. So this is a mini version of the air-cooled condenser here, which I'll discuss shortly. On the center lines, for example, there's 8 bearings in the machine with lube oil on them. A lot of heat is extracted through the lube oil. So triple CW system, we call it, is the closed cooling water system. This is the cooling for the cooling water. This circulates around the site, extracting heat where required. These tanks here, these are our distillate tanks. So this is equivalent to 1 day's running on the site. This is a standard GE model. Like you could literally visualize this plant in a different country, whereby you might need to actually treat the distillate fuel as it comes in, like filter it before it goes to the treated tank. We're fortunate that with the refinery next door, so they should comment, this is quite photoshopped. The refinery doesn't look like this nice green field, but with the refinery next door, when the supply comes in, the fuel is good enough to go straight through the machine. The handy thing with having 2 tanks is we don't run that often on secondary fuel. And with having 2 tanks, we can actually circulate the fuel and keep it fresh. And finally, just this structure here, this is the air-cooled condenser. So we'll go through the water cycle, but when you pass through the steam turbine and the steam needs to return back to condensate or water, this is used to basically condense it. We are close to the harbour, but from Whitegate village up to the site, you climb about 38 metres. And during the construction planning phase, the cost to put a pumping station down at the shore to pump up cooling water versus the efficiency gain, it wasn't worth it. So what we have here is we've the air-cooled condenser structure. I suppose one thing it does help is keep the site, the footprint of it quite neat. So like what's coming in really is just gas, water, what's going out is electricity. So what I'll do is I'll start explaining now how the actual machine works. And we'll start off with the compressor. So air will be sucked in through the filter house here. There's 2 stages of filters. The filters out at the front really is to stop coarse material such as leaves, airborne debris from entering the machine. And then as you get into the next phase, they're quite fine. It can, it'll block pollen, airborne pollution. It's a maritime environment, so salt, etc. will be blocked. So a bit like the requirement for the gas fuel to be heated up and also the water to be of a very clean quality, we need the air as clean as it can be as well going into the machine. So we'll just step in here to the turbine hull. and I'll start off with the gas turbine. So this is the picture, again, gas turbine up on the 96-wheel trailer during the construction phases to give you an idea of the size of it. And I'll just start the animation here. So to give you a feel for the size, you might see this guy here's average height. It'll give you an idea of the size of the unit. So I'll just get this rotating. So what we've done so far is we've drawn air in through the filter house. It's about 600 kilos per second, or I suppose 2,200 tons of air per hour is what's coming into the machine. As it comes in through the filters, you get a drop in pressure and temperature. During operation, something we do keep an eye on is the differential pressure across the filters. If the filters are starting to clog, the differential pressure will increase. So that's a kind of a performance metric you keep an eye on. As the air comes in, there's 18 rows of blades. So the number of stages of blades will give you an idea of what level of compression you'll get on the air. So it comes in at atmospheric pressure, maybe just a little bit down from it because of coming through the filters, and it gets squeezed then through each row of blades. So each blade, there's a lot of analogies here with an aircraft. There's an airfoil shape on the cross section. So this is designed to catch the air coming in. You get a downward force, which will start to turn the shaft of the machine. The last thing you want in a compressor is any kind of turbulent flow of air. So as it passes each stage, it'll go through a little set of nozzles, or other people might call them diffusers, which helps straighten the air back up. Hits the next stage, downward force again, and it keeps straightening up and getting rotated as it moves all the way down. So while you start off here, you know, atmospheric pressure maybe just a bit down from it. By the time you get to the end of the compressor section here, the discharge pressure is up maybe at 17.5, 18 bar pressure. The other thing to bear in mind is if you ever get a bicycle pump and you put your hand over the end of the pump, and you attempt to squeeze it, you'll feel heat on it. So by squeezing the air down, we've also added heat, and we're now up to about 400 degrees Celsius as well. The machine is designed to run at 3000 RPM. So if you divide 3000 revs per minute by 60, you get 50 pulses per second. So that kind of correlates with the 50 hertz system in Ireland. Next, we get to the power turbine. So this is what we'd refer to the 3 stages of blades here. So this is the gas turbine itself. And I'll just bring in the gas fuel. So the flow rate here is about 50 tons to 55 tons, depending on I suppose, the loading on the machine. This is what the combustion can looks like. Quite a lot of pipe work on it. I suppose bear in mind it's a dual fuel unit. So when it's operating in gas, there's also atomizing air being fed to the combustion can. And then when we're on secondary fuel, there is distillate fuel primed to the combustion can as well. But also when you're running on distillate fuel, you also have to bring in water injection, which is, I suppose, close to a 50-50 ratio. The combustion temperature on the gas fuel is up around 1400 degrees Celsius. I suppose gas fire stations would be referred to as clean technology, and I suppose by having the combustion temperature that high, you greatly reduce the amount of NOx emissions. So, so the gas fires down the chamber here, and the first stage of blades will, I suppose, experience the 1400 degrees Celsius, but there is a trick to help the blades a little bit. As part of the air coming in through the compressor, there's actually cooling holes in the blades. So some of the air gets siphoned off in through the rotor here, up the top of the blade, and it comes over the top of the surface. So you have 400 degree air sitting on the surface of the blade. So the blade itself isn't experienced to the full temperature of the gas, but obviously it's a very hot environment, and they're very, I suppose, exotic metals being used here. The life cycle of the blade is roughly every 24,000 hours, we'll change them out. Or if you're in a starts environment, that would equate to about 900 starts. So as you get from the first stage, same idea again as the compressor, it'll go past the blade. GE call the blades buckets because I suppose a bit like a more pronounced aerofoil pattern on it. Excuse me, it's designed to capture the hot air gas and get a rotation. So again, it'll go through a nozzle, straighten up, hit the next set of blades, rotate again, the next nozzle, and finally after the third stage, it's out into the exhaust. Now bear in mind, we've had 1400, maybe 20 degrees here, and we're down to 650. So it's quite a drastic drop in temperature. So that's really the energy conversion. Here's what you're seeing through the heat loss. And the gas turbine is approximately 2/3 of the power of Whitegate. So it's a 280 megawatt gas turbine. If ambient conditions are favorable, you'll actually get more power out of it. So a gas turbine likes high pressure, kind of low temperature. So those kind of still frosty winter's days when, you know, there mightn't be any wind, you'll see Whitegate, you know, in commissioning, it actually got up to 460 megawatts. But during the summer, the density of the air is a bit less because it's warmer. That will derate the machine a bit. So what you'll find is in normal operation, the guys up in the control room at Whitegate, there is a console called the EDL platform. It's electronic dispatch instruction logger. They will declare the unit as ambient conditions change. And I suppose this tool then is also used for the grid to send instructions down, be it for energy actions like megawatts up and down the range, or maybe to provide voltage support in the area through megavar instructions. So quite a dramatic drop. And I suppose on the exhaust flow itself, it's at 650 degrees. The flow rate, so you've had, I suppose, 2,200 tons per hour coming in on the air, added with a bit of gas. So you're up around, you know, 2,250, 2,300 tons. And the other thing to bear in mind, this is swirling at 3,000 RPM. So there's quite a lot of energy still in the exhaust of the machine. Now, I suppose back in older generations of machines, if you had an open cycle gas turbine, a lot of this energy would have just gone up the stack. But what gives a unit like Whitegate and the other CCGTs in Ireland the, I suppose, efficiency gain is this heat then is going to be used in the boiler, which we'll discuss next, to convert water to steam, and then we'll bring the steam to the steam turbine. So we'll just move to the HRSG next. So this is basically a giant kettle, which is probably, you know, it's a boiler, but they call it the HRSG, which is the heat recovery steam generator. So the boiler at Whitegate is quite big, I suppose. It's probably 40 to 50 meters high, up to the drum level up here. So we'll just get this animation working here. So the exhaust gases come out of the gas turbine. Bear in mind, as it's running, this is almost like a hot tornado. So the 9FB machine we have is quite tough on the first stages of tube bundles, which is our high pressure superheater. So I suppose part of our maintenance inspections is we always go in and have a look and see is there any bracing needed or how are the baffle plates, because you don't want the hot gases escaping on the side of the tubes because you'll start getting differential heating on the rest of your tubes here. So it's a horizontal flow boiler with vertical tubes. There's 18 modules in total. It's a triple pressure system. So you have a high pressure, which is 140 bar. Intermediate pressure is about 27 bar, and low pressure is about 4 bar pressure. To put that in perspective, I suppose your car tire is about 2 bar pressure. So the HP circuit in particular is very high pressure. We actually have duct burners as well. So we bring these in at the top end to, I suppose, to help increase the output of the unit, but also they're quite handy for the unit. It helps it to provide reserve. So what happens here is the duct burners come in, it fires the gas, and the temperature actually increases to 750 degrees. This increases the temperature and pressure of the steam, so you get higher pressure steam flowing to the steam turbine. The steam turbine is normally about 150 megawatts rated, but it can push up towards 180. So that'll get you 280 on the gas turbine, plus 150 is 430, but with the duct burners, you can get a lift of 20 to 30 megawatts, depending on, again, on ambient conditions. Now, as it goes through the boiler, the temperature going up the stack is 80 to 90 degrees. You don't want to drop the temperature too low because you still need a bit of energy to get the gases up and out. If the temperature is a bit too low here, you might lose a bit of buoyancy and you wouldn't make it out the top of the stack. Now, we've given, you know, tours to the site, and you can generally, I suppose, supplement the only 3 slides here with the site tour. But in the absence of the site tour, I actually put together a couple of slides to try and explain this a bit better for you, because there's statements here like triple pressure system, it's more efficient, but when you just look at it like this, you mightn't fully appreciate that. So I'll just step back here. Excuse me. So we go to the HRSG. So I can't be accused of plagiarism. This is definitely my own drawings when you see the next bit here. So on our y-axis here, I have temperature, and as you go up, the temperature increases. On the x-axis is the addition of heat. So as you go across, you're going to add more heat. So we'll, I suppose, use the analogy of, say, a kettle at home. So when you plug in your kettle and you set it off, this is the sensible heat section. So as you apply heat, you get a linear increase in temperature. And when you get up to this point here, this is known as the saturation temperature. This is 100 degrees Celsius. The kettle trips off and the steam's coming out the spout. If you were feeling a bit, I suppose, bored and you kept the heat or the on button on the kettle, eventually you'd end up with a dry kettle. The heat, you just convert all the water and it'll go out the spout. So you're kind of moving along this line here. If you trapped the output of the kettle, so you're kind of feeling a bit braver, and definitely don't try this at home, you'd actually start to build pressure as well as temperature, and eventually you get to this point in the curve where you have a kettle full of dry steam. You don't have any water left at the base of it. And if you keep supplying heat, the temperature starts to take off very quickly here. So this is now superheated steam, and it's dry superheated steam. So that's what we want to get into the steam turbine. We do not want to put wet steam into the steam turbine because it can lead to damage of the turbine blades and corrosion. So what do I mean then that by having a triple pressure system boiler, it's more efficient? So if by looking at the temperature profile, so you have 650 degrees at the GT exhaust, you can look up your steam tables. I hadn't seen steam tables probably since college, before I started this role in 2014. And if you look up the steam tables, what you'll find is for high pressure steam, saturation temperature over here is 337 degrees Celsius. For intermediate pressure steam at 27 bar, it's 230 degrees. And at low pressure, 4 bar, you're at 152 degrees. So what that means is you can take advantage of the temperature profile from 650 down to 85, and you can end up with 3 systems giving you superheated steam, which then can feed into a triple cylinder steam turbine like what we have. If you're to get the same steam flow, you'd end up with bigger pipes, be more capital expense. So by having this size boiler with triple pressure, you get more steam flow to your steam turbine. So I'll just go to the next slide here, and I'm going to try the magnifying glass here, see if this can help. So again, apologies there, I definitely colored this in myself. What we'll do is I'll just trace the water flow through the boiler, and you'll probably get a better appreciation then. So at the air-cooled condenser, the large fan structure, we've converted the steam down to condensate. The extraction pumps will pump, and it's typically maybe 420 to 440 tons per hour up to the boiler. So what they do is, as the condensate comes from the extraction pump, it'll go up through the low pressure economizers. So if you think back to the graph in the previous slide, we're coming up the sensible heat section, and it'll come up top and it'll go through a deaerator, which will attempt to take out any dissolved oxygen in the feed water. From here, it goes into, well, it actually splits. The total flow rate per hour at high output is 440 tons per hour. 40 tons of condensate feed water remains in the LP boiler circuit. 400 tons will feed down to the boiler feed pumps. For 1 second, because there's 400 tons of water sitting there. So the 40 tons of LP feed water, they come down through the evaporator section. So this is the horizontal section on the kettle graph, we call it. And in the evaporator section, you're separating out your water and your steam. So the steam comes out of the evaporator section and joins the top of the drum. From the top of the drum then, it'll exit and go to your superheated section. This is where your temperature profile in the boiler comes in. So, you know, the saturation temperature that you saw on the last graph, these are all at your drum. So the saturation temperature for LP is 150 degrees, 230 and 337. And from the LP superheater, this exits then and heads for the steam turbine. If we go back to the 400 tons that we parked for a second, they come down to the boiler feed pump. This is a multi-stage pump. So At 27 bar pressure, about 70 tons heads off up the intermediate pressure economizer. And of the 70 tons, about 40 to 45 gets diverted to the gas performance skid. So this is the water that's used to heat the gas going into the gas turbine. That's about 40 tons per hour. The remaining flow goes up to the IP drum and repeats the process into the evaporator. You separate your steam and water, join the top of the drum, from the top of the drum to the superheater section, and then out to the, well, not quite the steam turbine yet, but we'll come to that in a sec. And then finally, the HP circuit has the most energy. So there's a number of economizers. I've only drawn, well, there's only one drawn there. There's a number of evaporators, and there's 3 superheaters. The same process again. So you end up with your superheated HP steam, IP steam, LP all heading off towards the steam turbine. So I'll just move on to the next slide here. So in the absence of a site tour, I took in a couple of photographs just from the construction phase. So this is December 2008. This is the structural steel frame which supports the boiler. On the next slide, you can see one of the modules being lifted up. So each of these modules, I think they're 130 tons. They came in by heavy haulage by night, and there's 18 modules. So a module might be, you know, your superheater section, or it could be your IP economizer, but there's 18 of them in a row. Just moving on to the next picture here. It's a closer look at one of the modules. So in here, you can see the tubes that would be, you know, vertically in the boiler, and then you have connections. I'm not sure if that's the drain end or the end that connects up to the drums, but at each end there's connections to, you know, to complete the connections, I suppose. And here we have module 5 being lifted into place. So the duct burners are situated here after the superheater 3 on the HP circuit. And then finally, I think I have one more picture. So this is a good photograph. Here you can see the LP drum. This is the deaerator where the water passes up to get rid of dissolved oxygen, IP drum, and the HP drum. So from here, we'll head back to the interactive display, and we'll head for the steam turbine. Excuse me. So we'll just start this going again. So we'll start off with the high pressure section. I suppose one thing to note is the higher the pressure, the smaller the blades. So as you head to the intermediate pressure, you can see the blades are starting to get bigger. And this is the LP turbine. And the blades here are actually just over a meter at the final stage. I'll come to that in a second, actually. So the HP steam comes from the boiler. It's up around 130, 140 bar pressure, more like 560 degrees. And that's actually a little bit high. It's probably closer to 330, 340 tons per hour. When it flows through the HP turbine, and it's the same process like you saw in the compressor, where you have a series of blades catching the steam, nozzles straightening them up. You get a flow through, and when it comes out the exhaust of the HP, this is actually called cold reheat. So this is more like IP superheated steam now. It's drop temperature and it's drop pressure. At this point, we actually send this back to the boiler, to the reheat sections, and it joins with the IP superheated steam. So you have about 330 tons here. You'll have about 30 tons of IP, and once it comes out of the reheater section, it then comes back down as IP inlet. Now, again, apologies, these figures are a little bit wrong. The IP contribution on its own is 35 tons per hour, but you have to bear in mind it's actually joined up with the exhaust of the HP turbine. So it's this plus 330. So there's actually about 360 tons of steam per hour heading through the IP cylinder. And from here then, the LP steam comes in, which, you know, close to 30 tons per hour. So you're up to nearly 400 tons per hour of steam passing through into the exhaust of the machine. Two things to note here actually in the exhaust. One is this is operated under vacuum. This helps pull the steam through the machine. You don't want the steam starting to condense back to droplets because it'll damage the blades. And the second thing is this shaft, bear in mind, is spinning at 3000 RPM, and the length of the blade is about a meter here. So the tip speed on the blade will be in the supersonic range. And if that were to spin in air, you'd overheat the blades. So by spinning this in a vacuum, it helps cool the blades, but the best way to actually cool the blades is to get the steam through it. So steam at 300 degrees Celsius will actually act as a cooling agent on these blades. Something to bear in mind here is this is the turning gear motor. So when Whitegate, might get an instruction to come off from the grid. If it doesn't run for a few days, it sits on turning gear, which is typically about 4 RPM. And when it's on turning gear, this allows even cooling for the whole steam turbine rotor here. If you stop the shaft when it was red hot, you could get the shaft, the thermos to hog. It could actually bend a little bit. And that's a bit of a nightmare scenario, because that means the blades could actually touch the shell casing here. There's very fine margins because you don't want your steam escaping around the blades. You want to catch as much of it as possible. So there's very fine clearances between the blades and the shell casing. So when the unit comes off, it goes onto turning gear, and it'll sit there for about three to 3.5 days until it's cool enough to take it off turning gear. So that's the steam turbine. I will just move out to the air-cooled condenser and just show you how we condense it back to steam. So this is the back end of the steam turbine here. It'll come along this duct here, up these pipes here, up to the top header. And I'll just get the fans moving here. So this is our air-cooled condenser. There's 20 fans arranged in 4 streets. There's 5 fans per street. And what happens then is, once the steam comes along the top, it'll go down through these little tubes, and it collects here as condensate, and it'll feed into one pipe down into the condensate receiver tank here. I suppose one thing to bear in mind is when the machine is at lower output, not all the fans need to be in service, and as the machine picks up, you should have at least 19, maybe 20 fans in place. But in the winter months, even if the plant's at a higher output, because ambient conditions are good, ambient conditions are also good for the cooling. So it's probably the summer months, if all the fans are available, you'll typically have a lot of them running when the plant's up at a decent output. So all we've done so far really is talked about rotational power, and we haven't discussed yet electricity. Now, I'll come to electricity generation on the generator in 1 second. I just want to hit this powertrain here just to give you an idea. So this here is the complete powertrain, and just something to bear in mind is there's 8 bearings in the machine. So there's a bearing here inside an exhaust. We have a bearing here just before the load coupling. There's a bearing either side of the generator. There's a flex coupling between the generator and the steam turbine. What that allows is a small bit of give in the axial direction, so that if you have to lift out turbines, the whole thing isn't rigidly bolted together. So there's a little bit of give between the generator and the HP turbine. There is, so that's bearing 5, we've bearing 6 here, we've a load coupling, and bearing 7, and finally bearing 8 is inside in the condenser of the machine. So when the plant's in operation, the reason I'm mentioning bearings, but there's a lot of stuff you'd monitor there, like the bearing metal temperatures, vibrations. They can tell you a lot on the health of the shaft itself, that it's all correctly aligned and there isn't any issues starting to develop. So just come back over here and we go back to the generator. So the generator for Whitegate, it's a single shaft machine. It actually sits in the middle between the steam turbine and the gas turbine. So again, I'll just get this thing to rotate. I'm going to explain electromagnetic induction a little bit better in a second. So what we just take out of this slide is the rotor winding, like it says in the tin, it rotates. So this is at 3000 RPM. There is brush gear here through carbon brushes onto slip rings. So this is where your DC current comes in and excites the field current, which is your rotor, and this makes it a permanent magnet. The stator windings, they don't move, so they're called the stator windings. These are actually, when the plant is synchronized to the grid, this has the electric field of the grid. So this is what connects to your 3 buses for 3 phases and is brought out to the step-up transformer to the grid. So what I'll do is I will finish now with this interactive. I'll just move back to the slides and just give you a little bit more on electromagnetic induction. So I found a GIF which kind of helps explain this a little bit better. So I suppose, look, electromagnetic induction is the process in which a conductor, if you put it in a particular position, whether it's rotating or it's stationary, but there's a magnetic field around it that's rotating, you'll induce currents in the coils. So that's kind of what's happening here. In this example here, you can see the carbon brushes on the slip rings. So this is how the current is being transmitted in. I suppose, as I kind of mentioned for Whitegate, it's a little bit back to front in that the magnet is the rotating part and the coils where you're inducing the current is the stationary part, the stator winding. A few other bits and things to kind of bear in mind when the unit is synchronizing to the grid. So as the machine is running up, you close the circuit breaker, you do a sync close, so the rotation of the shaft is matched with the grid frequency. So ideally you're at 50 Hertz, and the machine's at 3000 RPM. And what happens then is the machine, I suppose, block loads. So what happens is it doesn't just linearly ramp up 0, 1, 2, 3. You might jump on and straight away you're supplying 20 megawatts. And then from there, as the mechanical power increases on the gas turbine, initially only, you'll start to open up like a power angle. So I'm trying to get this right in the camera like this. As the angle between the rotating field of the rotor and the grid starts to open up more, you actually push out more power then. So I suppose other bits and pieces with the generator, if the grid, for example, wants Whitegate to produce megavars lagging, the operator can increase the field current. So the excitation increases here and you'll over-excite the machine. If you need to do the opposite, where maybe at night time you need to bring down the voltage, say in the Cork area for where Whitegate's connected, the operator will reduce the excitation, the machine will become under-excited and you'll start to pull megavars in. The limits of how much you can pull in is limited by the size of the rotor winding, and conversely, when you're exporting megavars, it's limited terminally by the size of the stator winding. So typically, a machine like Whitegate can do maybe, Whitegate can do 290 megavars lagging, but only say 180, 190 leading. So there's a slight skew there, but it's a useful, I suppose it's a useful DS3 product for the grid in terms of controlling the local voltage. So that's kind of it really on the generator itself. I just have another couple of pictures to finish up. Actually, there's probably one point I should have mentioned, and I'll just go back to it, if you don't mind. On the gas turbine, when we were looking at the Rock-Off project, a lot of our discussions was happening in here. There was two aspects to demonstrating compliance, for that project for grid. One was the mechanical integrity of the unit. So if you think, right, as you get more renewables onto the grid, and you might have to take off some thermal units to make space, there's going to be less inertia in the system. So if there's a system disturbance, the system frequency can fall faster, harder. So if you take, for example, each hertz is 60 RPM. So if you went from 50 hertz to 49.5, you've lost 30 RPM off the machine. That mightn't sound like much, but when you add up the weight of the gas turbine, the rotor of the generator, and the steam turbine, you've about 300 tons spinning at 3000 RPM. And in a couple of milliseconds, you've taken 30 off. So that's huge mechanical stresses on the couplings. So we had to demonstrate the machine could take that. The other aspect though, with the compressor is when you're at 50 hertz, the machine is at 3000 RPM, that's fine. So air is already in the compressor. But if the grid speed suddenly drops, you've lost 30 RPM, you're now taking in air at a lower pressure. What the risk is the air that's already in the machine at the higher pressure, you could get a surge. So what happens is on a unit like Whitegate, there's bleed heat. So you're always bleeding some air back into the inlet. And when you get to base load, that closes up. So the other thing I should have mentioned, just thinking of it, is there's inlet guide vanes here as well. So before you get to maximum output, the airflow can be controlled as well through the guide vanes. So through the guide vanes and the bleed heat, you try to minimize any turbulence in the compressor. But generally, like during an under frequency event, what will happen is the machine will slow down. So what the machine initially will try to do is it'll try to make up for the loss of air by increasing the gas fuel in. But there's limitations in that because you don't want your fuel mixture too rich. And also by adding more gas, you're going to increase the pressure here, and the compressor might not allow that. It'll say, look, the pressure on the discharge end is getting a bit high. So the bleed is going to have to open again. So that's just kind of a little flavor that, look, the machine, you know, we're talking operating at 3000 RPM, which is the design. But what we're seeing is more and more discussions about what's happening when the frequency isn't quite at 50 hertz. On the flip side, if the frequency is very high, your machine will speed up, you'll pull more air in, the governor on the machine will try to back off the gas because it'll govern, and you run the risk of getting a bit lean, and worst case scenario, you get a lean blowout, you'll extinguish the flame and the unit will trip. So these are all considerations, I suppose, that we had to look at when we were doing the rock-off study. So I'll just head back there to the generator itself. So that's just a picture of the generator coming off. This is actually the jetty ESB, so they're very good neighbours to allow Borgosh Air at the time use the jetty to get some of the barged equipment off. So the generator in that, I suppose, unconnected would be 280 tons. It's a bit heavier in operation because there's huge losses on the stator winding, so it's actually hydrogen cooled. So in operation, it's filled with hydrogen, and you've seals then at each end, so you don't want the hydrogen to escape because hydrogen at the wrong purity is lethal. This is it coming up the road. So in the background, actually, you can see the 3 open cycle units the ESB have at Ahada. This is the main step-up transformer arriving at site. So it's a 560 MVA transformer. I suppose there's bigger ones than some of the 400 kV stations, but there's quite a big transformer. Its weight there will be 320 tons, but that isn't full of oil yet. So once it's commissioned and filled with oil, it's a lot heavier. The oil's in there to cool the windings. It's 19 kV up to 220, like we mentioned, but there's also a tap changer on it. So you can control the voltage using the tap changer as well, and also maybe in parallel with the machine. And this picture I showed earlier on, but just on a bigger version. All the footpaths actually had to be taken up just along this bit here to let this pass up. And the wall was surveyed. Thankfully, it didn't fall in because it would have been an expensive mistake. And then the footpaths were made good afterwards. So that's probably it, I'd say, from me.
Thanks, Rory. There are a few questions at this stage have come in, and thanks, by the way, for an excellent lecture. I just have a question myself in relation to the electrical end of it. You mentioned earlier you had 2 feeds coming into Whitegate, 2 from ESB. If you have one of those out for maintenance, what's the situation then if you had a failure on it? Do you have an alternative supply ready?
If one feeder is on maintenance and the remaining in-service one trips, yeah, we're in trouble. There is a 20 kV supply that comes into the site, but that's purely just to feed the house load. So like, for example, if the main transformer was switched out for maintenance, we can switch over to the local distribution network at 20 kV, but that only feeds you know, the small load like you might have during an outage. So yeah, if the cable trips and we're on a tail feed, we're in serious trouble. It'll be a very severe trip in the plant.
The question came in then in relation to blackout. If you did have a blackout, what is the situation then to restart?
So the station itself would have its own black start procedure. So I suppose there's a few scenarios. It depends on the nature of the blackout. During commissioning of a plant like Whitegate, it's expected to be able to trip to island mode. So what that means is, let's say the 220 kV breaker opened on the transformer, the unit should be able to drop back and just feed its own auxiliary supplies, so maybe 4 or 5 megawatts. And it should be able to hold that position until the grid instruct to maybe resynchronize across the 220 kV breaker. So that's one scenario, and the unit was tested during the commissioning phase. If the nature of the blackout was that the station ended up blacked out as well, so let's say the breaker didn't open on the connection point, but just the voltage collapsed in the southern region, then there's a couple of things that will depend how quickly something like Whitegate can come back. So you'd have to check the integrity of the plant, but also then you're kind of looking at areas like the boiler. Have you retained drum levels? If you haven't retained your drum levels and it's drained quickly but hot, then you won't be able to put new feed water back into the HRSG because you could cause a thermal shock. So the plant could be out, you know, for a number of hours. Then you could be out for 12 hours.
Okay.
If you have saved the drum and the plant is blacked out, then what would happen is Whitegate would need an external supply to restart it. So as the unit's spinning up, like the generator itself is quite large. It's a 535 MVA generator. to, I suppose, on an electrical thing, if you start any motor, you get a very high inrush current at the start because there's torque to overcome once you get the machine turning. So when Whitegate is running up to synchronize, you can suck in up to 18 megawatts of house load while the line commutated inverter is actually bringing that generator up to synchronous speed, up to 3000 RPM. So we would need a supply external to the station that's at least 18 to 20 megawatts to start up Whitegate. So thankfully, the ESB site down the road is a very strategic site. It's one of the black start stations of Ireland. So on that site, they have diesel generators that can start an open cycle gas turbine. They could maybe synchronize a second one. There is black start up at the Lee station, just west of Cork City. So historically, they'd try and bring a supply from Lee to the Marina station in Cork City, bring a supply up from Ahada. They'd synchronize the two stations there. And once they start building stability, then they might start considering bringing on something like Whitegate. But it would be at the instruction of the control room and EirGrid and Sony, and they'd have to decide the nature of the blackout and is it safe to bring in 80 megawatts quickly, because the risk is if you bring it in too quickly, you could collapse the whole thing again and you're back to square one.
Mm-hmm. Okay, from Adam Doyle, does the auxiliary boiler have any role in preheating the gas during a sink?
Does the auxiliary boiler? That's a good question. It would actually, because it provides IP steam, which is the mode of steam to pull the vacuum. Actually, I didn't mention how we pull vacuum. We've steam jet holding injectors, so you need IP steam. So yes, the auxiliary boiler can support preheating the gas.
Okay.
That's a good question.
From John Coleman, what is the overall efficiency of the turbines at full load?
The overall plant, I suppose it depends on ambience, but like you could be anywhere from, you know, depending on your gas usage and the ambient conditions, you could be between 57, 58, 58 and a half. It depends on the ambient conditions and a lot of that. On the compressor isn't the most efficient machine actually. The compressor itself is about 40% efficiency. The gas turbine, if it was open cycle, would probably be 38, 39%. And the steam turbine efficiencies are quite high. I haven't checked them now in a while, but the steam cycle would be well up into the, you know, I think the 80s, 90s. I'll have to double check, but it's the steam cycle that kind of brings up the overall plant efficiency. It kind of punches above its weight.
Right. From John Coleman, how much does the drive shaft expand in length at full temperature?
The drive shaft, I think that is noticed more on the IP-LP turbine. I'd have to double check. I think it's about 25 tau, but I'd have to double check that. I suppose if John can be a little bit kinder to me as my electrical background, but I think it's of that order. Certainly when the machine runs up, you do get movement on it and it'll expand. And I suppose diff expansion between the shell and the rotor is a key parameter you'd watch.
Okay. From Lee McFadden, what is the annual load factor for the station?
It varies. So it kind of depends on your outage year as well, but you could be anywhere from, you know, if there's a lot of wind, your load factor could be down at 50 to 60%. But yeah, Whitegate typically will be up around maybe 7,000 hours, 6,500, 7,000 hours, and averaging in the 60s for your load factor.
Okay. Does the station from Nanjiao, does the station always output 450 megawatts? And
no.
No. And
no.
How many generator sets are in the station?
So it's a single shaft machine, so there's only one generator. That's probably something I should have touched on. Other configurations might be a dual shaft machine would have a generator on the gas turbine and the steam turbine, and the output then is collected, I suppose, at the step-up transformer. But at Whitegate, it's a single shaft arrangement, so only one generator.
Okay. A question here from Nanjiao again. Does CCGT provide primary frequency response?
Yep. So it's a synchronous machine, and currently there's 12 DS3 products out for available to tender for with EirGrid, and Whitegate can provide 11 of them. So it provides fast frequency response primary all the way through to tertiary response at 20 minutes. So it's a synchronous machine with a governor, so it naturally governs as well.
Fine. Okay, question from Anju. Can you please explain what H or SG stands for?
So that's the heat recovery steam generator.
Okay. From James Doyle. In the LP boiler, what is the process for removing the oxygen from the water?
So that's up at your deaerator, your dissolved oxygen. So from memory, the water comes in the top and there's like a series of plates. And as it hits down through the plates, it releases the gases, being water, or sorry, oxygen is one of them. And then they get vented out the top.
Okay. From James again, what is the station power consumption overhead in that, and which power does the station itself consume?
So typically 1.5–2% of, so for example, if Whitegate was exporting 440, it's probably generating 450. So that would be, yeah, 1.5–2% of the gross power is consumed.
Okay, I'll just take one or two more questions at this stage. We're running over a bit. What is the annual maintenance for the boiler, turbine, generator? Does maintenance incur much download time annually?
So it depends. There's two things that drive the outages. One is what stage you're at on, say, the gas turbine with your intervals. So, every 24,000 hours, you'll have to go into a hot gas pad inspection. And every 48,000 hours, you're into a major inspection. In the years in between, it's just a 1-week borescope inspection. So that's one aspect of it. The other thing that's in parallel is you've written scheme of examination. So there's a lot of high pressure vessels on the site. They have to be inspected through statutory inspections to make sure they're safe, especially you're up at 140 bar pressure. So they typically would have to be done each year as well. So they're done in the shadow of whatever inspection is on. So, and then I suppose then you look at opportune maintenance. So for example, in 2020, Whitegate would have been planned for a 1-week outage. You would look at what other jobs you can get done around the site and coordinate all the permitting to take, the various pieces of equipment out for maintenance. Yeah, that's probably it.
Okay, is the switch from gas to distillate fuel seamless and vice versa in the combustion section?
So yeah, we can switch seamlessly at 180 megawatts from gas to distillate. If you were to push up, you need to bring in your water injection then to suppress your NOx emissions. For the unit to switch back from distillate to gas, we can't do that at our minimum stable. So we have a derogation with the grid. We actually have to drop down to approximately 25–30 megawatts on the gas turbine. And when the fuel rate is lower on the distillate, at that point, then you can switch to the gas fuel and bring it back up. And there's another feature actually, Chris, as well. If for some reason the pressure dropped on the gas network, the machine will attempt to switch over to distillate at any output.
Okay. Okay, final question from Eamon Sheehan. How is the output power physically controlled? Is there direct command from air grid to the generator?
Yeah, so the unit will follow grid instructions, but the output will move around that instruction as well. So like let's say it's at 390 megawatts and the frequency is below 50 hertz, the unit will govern to attempt to correct that itself. So it has a 4% droop setting on the governor. So
Okay.
that's fairly common across the units like Whitegate.
Okay. At this stage, I'll pass back to Aidan Langley.
Thank you, Chris, and thank you, Rory, for addressing those questions. And and also thank you to everyone that put in a question. And I could see they were all streaming in there. So sorry if you asked the question and we weren't able to get to it. Because it's as Chris said at the top of the talk, it's actually a joint exercise between the Institute of Engineering and Technology and Engineers Ireland. So as the chair of the IET in Ireland, I'd like to pass it across to the chair of Engineers Ireland in Cork, Rory Keane, to propose a vote of thanks.
Thanks very much, Aidan. So look, I'd like to just start off by thanking the IET for inviting us to co-host, yourself, Aidan, Chris and Jeffrey, and also to Michael O'Donovan, our own committee, who generally liaises with you. I think the number of participants online, which was certainly over 150 anyway, is kind of, I suppose, both a testament to the interest in the topic, and also, I suppose, is kind of silver lining to our current situation with COVID-19, and that people are becoming more used to the online environment. So Rory, thank you very much for an excellent lecture. You have a very relaxed presentation style, but I think this belies a deep understanding of the topic of the plant in question. And I think this was confirmed by, the ease with which you answered all the questions in the Q&A. Also the interactive presentation was excellent. Again, for somebody like myself, kind of coming from a civil background, it explained the topic very, very clearly. So on behalf of myself, representing Engineers Ireland and also my colleagues in the IET, I'd like to, again, congratulate you and thank you very much. I'm not sure if we were having an in-room event. I typically at this point call for a round of applause, but I'm not sure what what we do in the online environment. But certainly, thank you very much, and I'll give you a clap myself. So I think I'll hand back to Aidan again.
Okay, thanks, Ronan, and thanks, Rory, and thank you to everybody that's participated this evening. And hopefully, you'll get to tune in on one of our future webinars, either the Engineers Ireland ones or the IET ones. So thanks very much. And I think this is the bit where Chris turns me off.
I was just going to say that this concludes the meeting at this stage. So thank you very much for attending.